Welcome back to the deep dive. Today we're looking at something that's it's the engine room of the whole AI revolution right now.
Yeah, we're definitely going deep under the hood today.
Because, I'm not talking about the shiny chatbots or the image generators that everyone is playing with on their phones. I mean the actual literal plumbing that allows those things to even exist.
Well, I'd say it's less plumbing and maybe more like high-performance physics engine design. But yes, we are going deep into the machine.
Fair enough. High performance physics engine. I like that. So we are talking about context.
Right.
Because everyone in the industry is just obsessed with context length right now. We want models that can read entire massive code bases in one go.
Or analyze hour-long videos.
Exactly. Or digest a whole legal case file in one sitting without forgetting the first page by the time they reach the last page.
Which is the holy grail. But there is a massive wall stopping us from doing that chiefly.
Yeah.
And that wall is the attention mechanism itself.
Right. And this is the transformer architecture we always hear about, the T in GPT.
That's the one. And the fundamental flaw, well, maybe not a flaw, but the reality of standard attention is that it scales quadratically.
Okay, let's define that for the listener immediately, because the word quadratic just sounds like high school math trauma.
It does sound intimidating, but it's actually simple, though brutal. If you double the amount of text you feed the AI.
Like going from a 10-page document to a 20-page document.
Right. If you do that, the amount of work the computer has to do doesn't just double, it quadruples.
Wow.
And if you go from 10 pages to 100 pages, the work goes up 100 times.
So the cost basically creates this hockey stick graph. It goes vertical very quickly.
And it kills your memory, it kills your speed. That quadratic scaling is the ultimate bottleneck. But today, we are covering the paper that basically took a sledgehammer to that exact bottleneck.
Yes, we are analyzing FlashAttention-2. This is by Tridow from Princeton and Stanford. And this is a massive deal in the space because, the first version of this paper, FlashAttention-1, was already incredibly famous in the field.
Oh, absolutely. FlashAttention-1 essentially saved the transformer model from its own inefficiency. It was a huge breakthrough. But this new paper, version 2, this is about getting dangerously close to the absolute physical limits of the hardware itself.
Which is exactly the mission of this deep dive. We want to understand how we actually get to those 16K, 32K, or even 100K context windows without going completely bankrupt.
Right.
So let's get into it. But before we can really dissect version 2, I feel like we need to understand what the first FlashAttention actually did.
Yeah.
Because it fundamentally changed the way we think about GPU memory.
It did. And to really grasp FlashAttention-1, you have to visualize how a modern GPU like an NVIDIA A100 is actually built. It has two types of memory, and they are very, very different.
Right. We've used the warehouse and the desk analogy before on the show, and I think it fits perfectly here.
It's the best way to visualize it. So you have HBM, which is high bandwidth memory.
That's our warehouse.
Exactly.
Yeah.
It's huge. You could fit gigabytes of data in there. All the weights of the neural network, all the text you're reading. But relatively speaking, it's far away from the compute units.
Right. It takes actual time to walk over to the warehouse and grab a box.
Exactly. And then on the other hand, you have the SRAM shared memory.
Which is the desk.
That's the desk. It's right in front of the worker. It's incredibly fast, almost instantaneous access. But it's tiny. You really can't fit much on it at all.
So the problem with the old standard attention mechanism before FlashAttention was what? Just too many trips to the warehouse?
Constantly. Standard attention would calculate a massive matrix of numbers, write the whole thing all the way out to the warehouse, then read it back to do the next mathematical step, then write it back again.
So the GPU is basically spending more time just moving data back and forth than actually doing the math?
Exactly. It's like a worker who fetches one single sheet of paper from the warehouse, brings it to the desk, stamps it, walks it all the way back, and then goes back for the second sheet.
That sounds agonizingly slow.
It was. So FlashAttention-1 introduced a concept called tiling. Instead of doing the whole matrix at once, it breaks the input into small blocks or tiles that fit entirely on the desk, on the SRAM.
Oh, I see.
Yeah, so you grab a tile, you do all the math for that specific tile right there on the desk, and you never touch the warehouse again until you're completely finished with it.
So you completely eliminate the commute.
You minimize it drastically, and it worked beautifully. It made memory usage linear instead of quadratic, and it sped things up by, 2 to 4 times.
2 to 4 times, which is basically a lifetime when you're talking about AI training runs.
Huge savings.
So if FlashAttention-1 was this massive breakthrough that basically solved the memory traffic jam, why did Tridow need to write a sequel? I mean, ideally, shouldn't that have solved the problem entirely?
And that is exactly the hook of this new paper. Tridow looked at the performance of FlashAttention-1 and realized something was still really bothering him. He solved the memory problem, sure, but the chip itself was still, well, it was still waiting.
Waiting for what?
It wasn't crunching numbers as fast as it theoretically could. If you look at any GPU, it has a speed limit, a theoretical maximum number of calculations it can physically do per second. We call these FLOPs.
Right, floating point operations, basically the raw horsepower of the chip.
Exactly. Now, if you just ask a GPU to do basic multiplication, like standard matrix multiplication, it can hit 80 or 90% of that speed limit. It's just pedal to the metal.
Okay, that makes sense.
But FlashAttention-1, even with all that brilliant tiling optimization, it was only reaching about 25 to 40% of the limit.
Oh, wow. That's a huge gap. You're leaving more than half the performance just sitting on the table.
Exactly. It's like buying a Ferrari and finding out the engine is electronically governed to 60 miles an hour.
Right.
So FlashAttention-2 is the attempt to unlock that engine, to make this really complex attention mechanism run as fast as raw matrix multiplication.
Okay, so how do they actually do it? Because if the memory traffic to the warehouse isn't the problem anymore, what is holding it back?
It turns out it really comes down to work partitioning.
Work partitioning, which is fancy computer science talk for who does what.
Basically, yeah. You have to remember, a GPU isn't just one big brain. It's a collection of many, many smaller brains called streaming multiprocessors, or SMs. An A100 GPU has 108 of them.
So that's 108 individual workers out on the factory floor.
Right. And to get maximum speed, you need every single one of those 108 workers sweating. You need high occupancy. If half of them are standing around smoking a cigarette while the other half are totally overwhelmed, your overall speed drops significantly.
And FlashAttention-1 had a lot of workers taking smoke breaks.
It did. It had some structural inefficiencies with how the work was handed out. But there was a deeper problem, too. And this is crucial. It's the difference between matmul math and non-matmul math.
To matmul being matrix multiplication.
Yeah.
See, I just assumed all math was exactly the same to a computer, like math is math, right?
You'd think so, but not on a modern GPU. These chips have highly specialized hardware called tensor cores. And these things are absolute monsters at matrix multiplication. They chew through it instantly.
Okay, so the tensor cores are the Ferrari engine.
Yes. But for other mathematical operations, like dividing numbers or calculating exponents for the softmax function, the GPU can't use the tensor cores. It has to use its general cores. And those are much, much slower. The paper actually uses a great analogy to explain this.
His chef analogy, I love this one.
It really paints the picture. Imagine a master chef. This chef is a superhero at chopping onions. They can finally dice an onion in 1 second flat.
Right.
That's your tensor core doing matrix multiplication.
Incredibly fast.
Right. But this exact same chef takes 16 seconds just to wash a single spoon. That's your non-matmul math.
That is a terrible allocation of skills. You are paying a master chef to wash dishes incredibly slowly.
It is terrible. Now imagine your recipe instructions are literally chop onion, wash spoon, chop onion, wash spoon.
Oh, I see.
Your superhero chef is spending 94% of their time washing spoons. You aren't using their superpower at all.
And so FlashAttention-1 was basically washing the spoon way too often.
Precisely. It was interleaving the slow math with the fast math in a way that just bottlenecked the entire system. So FlashAttention-2 introduces 3 very specific tweaks to fix this chef's workflow.
Okay, let's break these down, because these 3 tweaks are really the core of the whole paper. And tweak number 1 addresses the chef directly, right?
Yes. Tweak number 1 is simply reduce non-matmul math. Specifically, they completely changed how they handle the algorithm for the softmax. That's the part of the attention mechanism that calculates the probabilities.
But you can't just not do the math right. You still need the correct answer to get the right probabilities at the end of the day.
True. You have to do the math. But you can change when you do it. In the original version, they were constantly rescaling the numbers at every single step of the calculation to keep the math stable. It was literally chop, wash, chop, wash.
Which is incredibly tedious for the GPU.
Right. So in FlashAttention-2, they realized they didn't need to rescale immediately every time. They could just keep a running tally of the statistics, specifically something called the log sumex. And they defer all those heavy rescaling operations until the very, very end.
So they basically just let the chef chop all the onions for an hour straight, and then they wash the spoon exactly once at the end of the shift.
Effectively, yes. They keep the math in a raw state for much longer and fix it in one go. This frees up the GPU to spend way more time in matmul mode, using those powerful tensor cores, and much less time stuck in the slow lane.
That's incredibly smart. You optimized for the hardware's actual physical strengths?
Oh.
Okay, so that's tweak one. Let's look at tweak number two.
Tweak number 2 is about parallelizing sequence length. And this directly addresses that lazy worker problem, the occupancy issue we talked about earlier.
So this is about making sure all 108 workers on the factory floor are actually busy.
Right. And to understand this, we have to get a little bit into the weeds of how AI training actually works. Usually, you train a model on a batch of data. Let's say 32 sentences all at once.
Okay, 32 sentences.
In the old way, FlashAttention-1 would assign one worker to one sentence. Worker A takes sentence 1, worker B takes sentence 2, and so on.
Well, that sounds perfectly efficient. 32 sentences, 32 workers. Everyone has a specific job to do.
It is efficient if the sentences are relatively short and you have a lot of them. Right. But remember, the whole mission here is long context. What happens when you are training an AI on a massive novel or a huge genome sequence?
The sentence isn't a sentence anymore. It becomes huge.
Exactly. And because it's huge, it eats up all your memory.
Yeah.
You can't fit 32 of them in a batch anymore. Your batch size drops all the way down to maybe just one.
So you literally just have one massive book in the back.
Yes. And if you use the old logic, you assign that one book to worker number 1. So what are the other 107 workers doing?
Standing around watching worker number 1 sweat.
Exactly. Terribly low occupancy. When context length gets huge, the batch size drops and the GPU just goes idle. FlashAttention-2 fixes this by parallelizing the sequence itself.
So instead of giving the entire book to one guy, they rip the book up into chapters.
Or even paragraphs. Yes.
Yeah.
Even if there's only one book, meaning a batch size of 1, they split that sequence into chunks and distribute those chunks to all the different thread blocks.
So everyone gets a piece of the action regardless of the batch size.
Exactly. All 108 workers can swarm that single long document simultaneously. This is totally critical for this era of long context we're entering. It ensures that even with massive inputs, the hardware is fully utilized.
It really just feels like a logistics fix.
It is. It's pure supply chain management, but for data. Now let's move to tweak number 3. This one is probably the most technical, but it solves a very specific communication bottleneck. It's called better warp partitioning.
Ooh, partitioning. We are definitely getting back into the Star Trek terminology here.
I know, the naming conventions are great. In NVIDIA terms, a warp is a squad of 32 threads that work together really tightly. It's essentially the smallest team unit inside a GPU.
Okay, let me make sure I have the hierarchy right. So we have the big workers, which are the SMs, and inside those workers, we have these smaller squads called warps.
You got it.
Yeah.
Now, the math of attention involves 3 distinct matrices. We call them query, key, and value, or Q, K, and V.
Right, the standard attention mechanism.
In FlashAttention-1, they used a strategy called split K. They took the key matrix, the K, and they split it across these different warps.
And that was a bad idea.
Well, it wasn't bad, but it had a nasty side effect. Because of how the math fundamentally works, if you split the key, the warps have to constantly talk to each other. They do a little bit of math, then they have to pause, synchronize with the other warps to add up their partial results, and then do more math.
Oh, it's the too many meetings problem.
Exactly.
You can't get any deep work done if your team has to sync up every 10 minutes.
That is the perfect analogy. Synchronization is incredibly slow, but calculation is incredibly fast. You want them working, not having meetings. So FlashAttention-2 switches everything to split queue. They split the query matrix instead.
And that somehow solves the meeting problem entirely.
It actually does. If you give a warp a specific set of queries, it can calculate the final answer for those exact queries completely independently. It doesn't ever need to ask its neighbor for help or partial results.
So it's just heads down work, no meetings.
No meetings. They do the math, and they write the final result exactly once. This dramatically reduced the read and write operations to the shared memory.
Wow. Okay, so just to recap the whole recipe here. 1, you do less slow math by deferring the rescaling to the end. 2, you split the incredibly long books into chapters so every single worker is busy. And 3, you split the work by queries so the internal teams don't have to talk to each other.
That is the FlashAttention-2 recipe in a nutshell.
The theory sounds incredibly solid. But let's look at the scorecard. Because theory is one thing, but did they actually hit the speed limit they were aiming for?
The empirical results are honestly staggering. In terms of raw speed, FlashAttention-2 is roughly 2 times faster than FlashAttention-1.
Just doubling the speed of something that was already considered a massive breakthrough, that is wild.
It is. And remember that Ferrari and second gear problem we talked about, the 25% utilization.
Right, where it was leaving all that performance on the table.
Well, FlashAttention-2 reaches 50 to 73% of the theoretical maximum throughput on those A100 GPUs.
73%, that's getting dangerously close to the 80 or 90% of basic raw matrix multiplication.
They basically close the gap.
Yeah.
They optimize the absolute heart of the transformer to be nearly as efficient as raw math. When they tested it by training GPT-style models with like 1.3 to 2.7 billion parameters, they were seeing training speeds hit up to 225 teraflops per second per A100 GPU.
Let's actually translate that into economics for the listener, because teraflops is a very abstract concept, but dollars and compute time are very real. What does this actually mean for someone out there trying to train a model like GPT-4 or Llama?
It fundamentally changes the unit economics of intelligence. Because the mechanism is twice as fast, it literally means you can now train a model with a 16K context length for the exact same price and in the exact same amount of time that it used to take to train an 8K model.
So you just get double the memory for free.
Essentially, yes. The context tax has basically been cut in half, and there's actually one more bonus feature in the paper for the chatbot developers out there.
Oh, let's hear it.
It's a massive optimization around causal masking.
Causal masking. This is the constraint where the model isn't allowed to see the future. Right.
When a model like ChatGPT is writing a sentence, it predicts it word by word. So when it's writing word number 5, it's allowed to look at words 1 through 4. But it physically cannot look at word number 6. It hasn't been written yet.
Makes sense. So in the mathematical attention matrix, half of the data is just, what, ignored?
It's masked out. It's strictly set to 0. But in the old way of doing things, the hardware would often still load those blocks of zeros from memory, do the math on them, realize, oh, wait, it's 0, and then move on.
Which is a complete waste of time.
A massive waste. FlashAttention-2 is actually smart enough to just skip those blocks entirely. It doesn't even load them onto the desk. For causal models like GPT, that specific optimization alone leads to a 1.7 to 1.8 times speed up, just from ignoring the zeros.
That is just efficiency stacked on top of efficiency. Now, I do want to point out, most of these benchmarks in the paper were done on the NVIDIA A100, which is the workhorse of the industry for sure. But the H100s are already rolling out everywhere, and I assume everyone listening wants to know if this works just as well on the newest toys?
They did actually touch on this in the paper, and it's real interesting because they didn't even optimize the code specifically for the H100 yet. They just ran the A100 code as is on the new chip.
And how did it do?
Even without using the specific new hardware instructions of the H100, like the Tensor Memory Accelerator FlashAttention-2, hit 335 teraflops per second.
Wow. So it just scales up naturally with the better hardware.
It does. It really goes to show that fundamentally good algorithmic design holds up across hardware generations. And the authors did mention they plan to optimize specifically for the H100's architecture next, which could unlock even more ridiculous speeds.
I also noticed a quick mention of MQA and GQA in the paper. We hear these acronyms floating around a lot lately: multi-query attention and grouped query attention.
Yes. We don't need to get too bogged down in the exact plumbing of those today, but effectively, they are architectural tricks to reduce the memory size of the key value cache during inference.
Inference meaning when you are actually chatting with the bot, not when you're training it in the lab.
Right. It makes the model significantly cheaper and faster to run in production for everyday users. FlashAttention-2 supports these variants right out of the box. It's really trying to position itself as the universal engine for all modern AI architectures.
It's just fascinating to me. We usually spend so much time obsessing over the model architecture itself. You know, is it a mixture of experts? Is it a Mamba model? But sometimes the biggest revolution is just better physics, better logistics on the chip.
It really is. And looking at this paper actually leads to a really provocative thought about where we go from here.
Oh, what's that?
Well, think about the progression we've just talked about. We went from standard attention, where the problem was it's too big for memory. Then FlashAttention-1 came along and said, let's tile it so it fits on the desk. Now FlashAttention-2 says, let's optimize the threads and the math so it's instantaneous.
And now we're sitting at 73% of the absolute physical limit of the hardware.
Exactly. We are rapidly approaching the speed of light for this specific architecture. There just isn't much more room to optimize attention on a GPU. We've effectively squeezed the lemon completely dry.
So what happens next if we want another leap?
That's the billion-dollar question. If we want another 10x or 100x leap in speed, we can't just optimize the code anymore. We either need entirely new hardware paradigms, totally different chip designs, or we need to finally abandon the transformer architecture entirely for something that is truly linear by design.
Ah, I see. If the engine is completely perfect, but the car still isn't fast enough for you, you just have to build a rocket instead.
Exactly. FlashAttention-2 has bought the transformer architecture a massive amount of runway. It's the literal reason we have these amazing long context models available today. But it might also be the peak of what is physically possible with this specific mathematical approach.
Well, until somebody actually builds that rocket ship, I'm pretty happy with 16K context windows. It definitely helps when you need to analyze a PDF that's longer than 3 pages without the AI completely crashing.
It's certainly nothing to complain about for now.
Tridow and his team have effectively done the impossible twice now. It's going to be very interesting to see if they go for a hat trick with a version 3 down the line.
I certainly wouldn't bet against them at this point.
Thank you for walking us through the nuts and bolts today. It's really good to look under the hood and see how this stuff actually works.
My pleasure.
Yeah.
Always happy to dig into the architecture.
And thank you to everyone listening. If you enjoyed this deep dive into the silicon heartbeat of your AI, make sure to check out the full paper. It's a great read. We'll catch you on the next one.